Hi guys, in this video I'll go over the pre-order depth-first search tree traversal algorithm. There are two main traversal algorithms, depth-first search and breadth-first search. Depth-first search goes into the depth first. That means starting at the root node, it takes the first path all the way to the first leaf node, then backs up, takes the path to the next leaf node, and so on. Breadth-first search, on the other hand, goes into breadth first. That means it starts with a root node at the first level, then traversing over the nodes on the next level, and then with the nodes on the following level, and so on. So it goes into breadth first. Now, depth-first search can be further classified into pre-order and post-order. Pre versus post focuses on a given node if the node should be visited before or after its children. In this video, I only focus on pre-order depth-first search. You can check out my other videos on post-order or breadth-first search. So pre-order depth-first search visits a node itself before the node's children. I assume in this case that when I visit a node, I simply output the node's value. And there are two ways to do pre-order. We could start at the left side and going all the way down, or we could start at the right side. Let's first start with the left side. So I visit 7, I output the node before the children, so I output 7, then going to the first child, which is 2, I output 2, then I output 76, there is a leaf node, so I cannot go further, I back up, visit the next child of 2, which is then 39, then go down to 11, it's another leaf node, so I back up 39. 39 doesn't have any more children, so I back up to 2. 2 doesn't have any further children. I back up to 7 and go to the next child of 7, which is 13. 13 is a leaf node, so I back up, go to the next child of 7, which is 45, go to the first child of 45, which is 83, then the first child of 83, which is 4. It's a leaf node. I back up, go to 23, back up, go to 18, back up, back up, back up, and then go to 31. And then I'm done. Now another way to do this is starting with the right side. So here again, I output 7, then I output 31. It's a leaf node. I back up, take the next child, which is 45, then go to 83, go to 18, it's a leaf, I back up, next child 23, back up, next child is 4, back up, back up, back up, next child of 7 is 13, it's a leaf node, I back up, go to 2, 39, and 11, then back up, and go to 76. Now in this video, I further focus on starting with the right side because it makes the implementation a little bit easier. Now for depth-first search, we always use a stack data structure. And we push nodes onto the stack and we pop nodes off the stack. So let's see how this works. We start out by pushing the root node onto the stack. Now with 7 on the stack, we continuously pop a node off the stack and push its children onto the stack, as long as the stack is not empty. So first I pop 7 off the stack. I output 7, that's the node I visit. And then I push 7's children onto the stack, which is 2, 13, 45, and 31. So these are now on the stack. Now I check again. Is the stack empty? It's not empty, so I pop a node off the stack, which is 31. 31 doesn't have any children, so no nodes get pushed onto the stack. Then again, I pop 45 off the stack. 45 has one child node, which is 83, so I push that onto the stack. And then check again, the stack is not empty. I pop a node off the stack, push its children onto the stack, which is 4, 23, 18. 4, 23, 18. And by now you can see that this output matches the depth-first search pre-order. We went from 7 down here to 31, then backed up, went to 45 and 83. Now the next node that we pop off the stack is 18, which is the node here. And then we back up, go to 23. So the output here that this produces is the pre-order depth-first search. 18 doesn't have any child nodes, so I pop a node again. 23 doesn't have any child nodes, I pop off 4, doesn't have any child nodes. Now I pop off 13, also doesn't have any child nodes, so I'm back here now. Now I go to the next node, 2, so I pop 2 off the stack and push 2's children onto the stack, which is 76 and 39. So 76 and 39. I check again, the stack is not empty, so I pop 39 off the stack. 39 has one child, 11. I push that onto the stack. Stack is not empty. I pop 11 off the stack. Doesn't have any child nodes. Now I pop 76 off the stack. Doesn't have any child nodes. Now the stack is empty and the traversal is complete. And this output here matches the pre-order depth first search. You can see we went from 7, 31, so match it to the output here. Then back to 45, 83, 18, 23, 4. So that's 18, 23, 4. Then backed up all the way to 13. And then going on the left side, 2, 39, 11, and 76. Now let's take a look at the implementation. So for the implementation, I use nodes that have 2 pointers. So each node has a pointer to its first child and a pointer to its sibling. So for the root node, the sibling pointer is null and the first child pointer points to 2. Then 2 points to its first child, 76, and to its sibling, 13. So the dashed lines here is the conceptual tree, and the solid black lines are the pointers. So 2 points to 13. 13 doesn't have a child, but it points to its sibling. 45 points to its child, 83, and to its sibling, 31. So this algorithm uses this type of structure. So initially I create a stack of node pointers and I push the root onto the stack. This is my starting point. Then I continue this iteration as long as the stack is not empty. So when the stack size is not 0, I take the top of the stack, which is now 7. You can see the stack here. I pop it off the stack, so that removes 7 from the stack. And then I output 7 to the console. Then I push 7's children onto the stack. So I get the first child, which would be 2. If 2 is not null, I push it onto the stack, so that pushes 2 onto the stack. Then gets a sibling of 2, which is 13. 13 is not null, so I push 13 onto the stack, get the sibling of 13, which is 45. 45 is not null, I push it onto the stack, get the sibling, which is 31, push it onto the stack, and then get the sibling of 31. This is null, so this ends the loop. And then I end up with this. I outputted 7 and I pushed 7's children onto the stack. Now I check the loop condition again. The stack size is not 0, so I take the top of the stack, which is 31. I remove it from the stack and I output the value. Then I get the first child of 31. 31 child pointer points to null, so child is now null. I don't enter this loop and I check again. The stack size is not 0, so I take the top of the stack, which is 45. I output it, and then I get the first child of 45, which is 83. So the child is not null. I push it onto the stack, and then I get 83 sibling. The sibling of 83 is null, so this ends the loop here. And now I'm at the output 7, 31, 45. Then I check again. The stack size is not 0. I take the top of the stack, which is 83. I remove it from the stack and I output the value. Then I take the first child of 83, which is here 4. 4 is not null. I push it onto the stack. Then I get the sibling of 4, which is 23. Child is not null. I push 23 onto the stack. Then I get the sibling of 23, which is 18. 18 is not null. I push 18 onto the stack and then get the sibling of 18, which would be null. That ends the loop. And then again, check that the size is not 0. Take the top of the stack, which would output then 18 and so on. So you can see that this small code uses the stack data structure to continuously pop nodes off the stack and push the children onto the stack. And this results in the output of pre-order depth first search. I hope you enjoyed this video. Thank you for watching.